So our next speaker is Rui Mao. He is a senior engineer and researcher at Alibaba. His research focuses on building predictable and high-performance data center networks by leveraging the programmable data plane. He received his PhD from USC. Please take it away.
Thanks for the introduction. And hi, everyone. This is Rui Mao from Alibaba Group. In this talk, I want to present our 2nd generation of storage network, which improve our storage network for the recent 5 years. And this is a joint work with our collaborators in Alibaba Group. First, I want to share some of the status we have for Alibaba Cloud. As we know that Alibaba is one of the largest cloud infrastructure in the world, and we serve for more than 2 million customers across 200 countries and regions with our computing resources in different regions and different availability zones. And we built our full mesh network to connect 2,800 CDN nodes with more than 150 terabit per second bandwidth. And our storage is massive, which store more than tens of exabytes data and tens of trillions of stored objects. So to support those huge storage is a challenge. And our architecture is so-called compute and storage disaggregation. So this architecture has been largely adopted by many cloud providers. So in this architecture, it separates compute and the storage into different clusters. So that's a lot of benefit of doing that. For example, each cluster, they can evolve independently, and then you can achieve very high utilization and lower the cost. And lastly, you can migrate your application across different compute clusters without worrying about your data. And for running this architecture, the compute traffic actually will go through virtual switch and be delivered to the within the compute clusters. However, when you want to access your storage, which will go through the storage agent, they do admission control and the storage virtualization. And the storage traffic actually being forwarded to the storage cluster and served by the block server, which is like a proxy to provide a storage service. And the data is then being forwarded to the chunk server and persistently stored into the disk. So in this architecture, we call the first network, which interconnect the compute and the storage as a front-end network, or F1, while we call the storage internal network as backend network, which is called BN. So from there, we can see that network actually become very important and actually is a bottleneck of the storage application, because all the storage operation actually will go through the network. So in order to serve the storage traffic, we should look at like what the storage traffic looks like. And this figure shows the timeline of the storage traffic over 1 week. And we can see that storage traffic actually is a majority in data center. We can see about 60% of traffic actually in data center are storage traffic. And it's also write heavy because the application want to use storage to persistently protect the data for data safety and the data integrity. And this figure shows the I/O distribution and RPC distributions for the storage request. As we can see that those requests actually are very short. And about 40% of the flow are up to only 4 kilobytes, which means that it can be transferred in just one round trip time without response to any like congestion control signals. So to sum up, we can see the EBS traffic is huge. But those traffic actually being spread out across the network for highly parallelism in application, for high availability and for tolerance. But from network point of view, those traffic is very challenging because it's both both bandwidth hungry and latency sensitive. So next, I will show our 2 generation of strategy to improve storage network. The first challenge we are facing is when the storage media migrate from HDD to SSD. In this case, the storage median latency reduced from tens of milliseconds to tens of microseconds. In this case, network becomes the bottleneck. In this case, we want to change the kernel TCP. So the challenging is that performance is not always win. So there are lots of dimensions we need to consider when we choose the protocol to improve. Thinking about the FN and BN, there are different situations. For example, we talk about scalability. In the FN, because they need to talk to different computer servers, the number of computer servers is massive. So typically, you want to ensure your high reliability and high performance, even you are facing tens of thousands of connections, even hundreds of thousands of connections. And those this FN network actually is across the different clusters, even across different data centers. So to enable this inter-data center accessibility, that is very important. Compared with FN, BN is very simple because you can always scale up your disk density, and then also we want to limit the failure domain. So in the storage cluster, it's only tens of servers in there. Next is about the interoperability. Because a different cluster you will build at a different time, they may have different hardware configuration, software configuration. And so the fundamental requirement for FN need to connect to different clusters that ensure this smooth connection so everyone can talk to the storage servers universally. Compared with that, the BN internal connection is always guaranteed because this hardware configuration is very consistent. So taking all these two differences, our choice is quite independent. For example, FN we choose a software solution because to satisfy this scalability and the interoperability requirement. For the backend, we have to choose the hardware to search for high performance. Then we design Luna. It's a user space TCP for EBS traffic. There are a couple of improvements compared with traditional user space TCP. First, we use a cross-layer optimization. We use run-to-complete model with zero copy, not just for the network layer, but across the network and the storage layer. And also we have lock-free and share-nothing thread management for both network pipeline and also storage processing pipeline. Then we released our new product called eSSD, which stands for Elastic SSD in 2018, which uses user space TCP Luna as a front end and RDMA for the back end. In this product, we achieve 1 million IOPS and 100 microsecond latency, and we use 4 core to support 200G traffic with 4 kilobytes blocks. This diagram shows in our production real data, we monitored the tail performance of 4 kilobytes rate, and it is coupled by the front-end network and the BN, and also SSD processing delay, and also SA, it's a storage agent delay. As we can see that by using Luna, our latency actually reduced by 80%. However, we still have we learned a couple of things after we deployed Luna. First, if we look at this figure, we can see that network latency has been gradually reduced by using Luna as a front end and RDMA as a BN. So the bottleneck actually shifts to the storage agent, which you need to run lots of computing heavy tasks. For example, CRC checking and also encryption and a per IO lookup. Those kind of tasks is very CPU intensive and also cause a latency hit. The next, we can see that in current stage, we already use 4 CPU cores, and when the network speed goes up, and we need more CPU core to keep up with the network speed. So it's inevitable for us to offload this computing resources to hardware. So next is about the network failure. When the failure happens, that the storage traffic will get dropped, then largely affect the storage application. So mitigating network failure is become very important for us. So in order to solve this problem completely, we are facing a new and a major challenge for the next generation to support the bare metal clouds, which will lead us to completely different and comprehensive solutions to solve the limitation we are facing. So currently, we have a hypervisor running in the host to support the virtual machines. And those hypervisor functions, including computing, network, and storage virtualization. And in the new generation, for these programmable devices, it allows us to run this cloud infrastructure services within this hardware, within this programmable hardware. So that's why we can provide the bare metal server to the customer, which provide the flexibility because they can run their own virtualization, even no virtualization at all, and they can run their own hardware platform. And especially for the edge computing, it's easy, like we just plug in a PCIe card, so it's very lightweight and fast for user to get cloud services. And it's also provided very good isolation and a security guarantee because you don't have to share with other users in this server. However, this creates a new challenge for running EBS because all the storage virtualization you should run inside this DPU, which is like a smart NIC. And this is an example because when the traffic goes through this DPU, it will go to the transport layer and go to the storage agent layer and then go back to the host. So they have two bottlenecks. First, you need to run this processing within the DPU's within DPU, and they are typically using WIMP CPU for saving the power consumption and the cost. And also, you are facing the limited throughput because the traffic goes through the PCIe bus twice. Ideally, we want to offload the data plan to hardware so they can directly go to the host and using control plan to running control functions. So how we can do that? So intuition here is that we have two goals. One is we want to offload as much as possible the data plan to the hardware, and also we want to change the path actively to avoid network failure. So that's why we want to use multipath. There are a couple of challenges. First, both the network and the storage layer are very complex software, and it's really hard to implement them in hardware. Especially the hardware is very resource limited because they use a WIMP CPU, as I mentioned, and also they want to use hardware for the network virtualization as well, like a VPC, virtual private network. And the resource left for storage is quite limited. And also we want to support multipath because each path will need independent resources. So the resources challenging is quite complex. And also the hardware, we want to offload the hardware, but we cannot completely trust the hardware because the major failure we are facing actually coming from this hardware. So how can we solve the problem coherently? So the idea is to fusion the network and the storage, because today we have a network layer and a storage layer at different layers. And when the packet comes in, we make network layer need to make the in-order delivery and do this packet to block mapping. So we need to do this mapping in real time. And also, when the packet gets lost and all the following packet cannot be delivered, which causes unnecessary head-on blocking. And our idea is to break the barrier and to make the packet to map to the data block directly. In this case, we have a field states, and when the packet gets lost, the following packet can deliver to the storage layer independently. And in this case, we don't have to use a large buffer, and also it's easy for running multipath because each packet actually is independent, and we don't need to touch the CPU and the memory. So here example we run for the read request, and the write is similar. When the user sends a request to the FPGA, and then they get the emission control, and also look up the virtual address for this storage request, and then they generate the RPC. And before generate the RPC, they will register the packet ID and the action into the hardware. And then the request get out, and when the packet come back, they will have the entry in the hardware already. And when the packet look at the table, and then they will automatically delete this entry after process this packet. After that, they will use the software to the double check because hardware may have the error happen. So we improve the performance to up to reduce the latency up to 40%, and also we work around the PCIe bottleneck. Over the 5 years, we improve our storage application by using Luna at 2019 and also Solar at 2021, and we reduce the latency by up to 72% and triple the IOPS. We have a couple of lessons we learned. First, that we're still halfway towards our final goal to offload everything, because when the CPU are running for the path selection and the congestion control, it's still very CPU intensive when the workload is high. And in the meanwhile, we think that work around the PCIe internal is a long-term requirement. That's require both offload the network processing and also application post-processing together into the hardware. For both two requirements, we advocate a new programmable hardware that can support us for the network transfer function and also for the application function. So in this way, we can design our customized application and the logic for running hardware offloading. And secondly, because we use jumper frame together with a multipass, this will cause the congestion even worse. Think about the example that even a single flow generate one packet for each pass. Given you have 4 paths, they will translate to about 12.8 gigabit per second bandwidth already. That makes the congestion control even harder. So our solution is we suggest using very fine-grained congestion control. There are 2 points here. We actually deploy HPCC after we published a SIGCOMM paper 2019. The first point is that we need to have the use a fine-grained congestion control to ensure the close to zero queuing delay. So that's very important because most of the traffic are very short. They don't respond to any congestion signal. So in this case, we need to make sure that when the packet comes in, the buffer utilization should be very low. And the second point, we make sure that the congestion control have the rate using rate control. So in this case, most of the cases we are facing like a window is less than 1. So we mostly using rate to control the traffic rate. With that, I'm happy to take any questions. Thank you.
Questions? I have a question, actually. So can you tell us a little bit about how the traffic is evolving? I mean, the workload, is it changing over the past 5 years? Where do you kind of see the workload going in the future in terms of what you're seeing on your system?
As we can see that the application traffic actually become very, very performance sensitive. Over the years, there are more application comes out, like database application to support the live video. And those kind of application is very like performance sensitive. In the past, we see the application like even a few second traffic black hole and application will suffer. Mm-hmm. So in the future, looking for like a shorter and shorter unavailability time, even within a second, they want to make sure the network connection is always on and performance is always high. Otherwise, they will experience long latency delay.
Is there a certain number of nines that you shoot for in your system, or you measure the availability?
Yeah, the availability is certainly 11 lines, but they also require the latency, the I/O latency.
Okay. Question there?
You said your read-write ratio was 1:4. How much of that is inherent in application writes versus the replication that you adopt?
So you asking how many of the write from the application?
Versus the fact that you must be maintaining multiple replicas?
Oh, so this write and read monitored from the client side. So it's from the application.
Just now you mentioned that 60% of the traffic is storage traffic. I wonder if this is common to almost any data center, or it's just specific to your own environment.
So based on our experience, there's a talk from Microsoft as well. They mentioned some similar number, like 60 or 70. They have even higher number, and from the Mark's talk a few months ago. Yeah.
Thank you for the information.
Okay, let's thank the speaker.